So let me just check if this thing is working. So we have done, so far we have been talking about algorithms, and we have covered at least one of the most popular algorithm, or the two, the TRPO and PPO. They're kind of the most popular algorithms. And currently, most under evolution process, like the model-based RN, which is really not yet, let's say it's not developed, it's open-ended still. So we have talked a little bit about it, but today I want to talk about, so there are always two exciting things about any subject. One thing is what's the latest and funkiest and whatever, like this TRPO or PPO, that's kind of fun bit. But the other thing is, what is there to explore? What is it that people have not yet cracked? What is difficult? Or what is something that has been a little bit, just a bit beyond? And so, of course, when you say something that's just a bit beyond, what is it up with this? Okay. When you say something that's a little bit beyond, you have to have at least some examples where it's been useful to think about it. So, are you guys familiar with the idea of a bandit? No. Okay. So then, anyways, this lecture will be anyhow useful because bandit is the oldest version of RL, let's just say. And so we'll cover this. But we'll cover this because in that example, we can understand the difference between what are these two words. Usually you might have heard of them, exploitation and exploration. So what do these two words mean? What would you guess? What does since you're just the two of you, this is going to be a conversational style class. Hi. So now we have 50% more people here. Okay, so what do these two words mean? What does it mean to explore and what does it mean to exploit?
Exploit is using what you already have and from which you know that it works.
Yeah, what you know works, right? And exploration is, well, it's finding out, right, if there is more. So there is, if you have, say, only a very limited time, should you explore? So what's usually called finite horizon or limited horizon, should you explore or should you just exploit what you know the best solution is? Just exploit. But if you have a long life to live, what should you do? Should explore and try and find the optimal solution. So this is the takeoff, and this is not easy to achieve. The problem, so we saw in the model, we saw last time the model-based RL, and the model-based RL was you get some data, so you take state, well as 0 A0, then you go to state, you get reward 1, state 1. I'm sorry, I cannot even order my letters today correctly. But yeah, you take an action 1, you get reward 2, blah, 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 blah. So there is no policy involved. You just collect this. You just live on your life, so to speak. You know, you are in this state and you take an action, you see what happens, go to the next state, take an action, see what happens. And then you say, okay, now I can take this as my input to the function. So this is my input. And there is this, I will look for a function f that outputs correspondingly for this state 1 reward 1, state 2 reward 2, and so on. So you look at this as input and output, and you want to find the best possible function. No. Sorry. What am I saying? I said something wrong. What did I say? So you want to find this function, so you have a model of the world. You could spend endless time figuring out the model of the world. But what you want to do is, so that would be the process of exploration, right? But what would you like to do is you take the limited knowledge, you have some data, and from which you construct some MDP. So you construct some MDP where you have decided this particular transitions are best, and some reward function is the best from your current data, and just exploit it. Just use that to generate more samples, to generate policy, to generate everything. So this is the exploitation. So you can go around wandering around the world forever, or you could just start exploiting what you know. So this process of exploiting from here, it becomes complicated. And in this generality, it is extremely complicated. Right? So we'll start with the most simplest situations where one can exploit. And that will be the situation of an MDP. So an MDP with only one state. So for the one state, whatever action you take, you will end up in the same state, right? So you don't need any state. You don't need any of the states to describe it, and you don't need any transition probabilities because you're going to end up in the same state, right? And you consider this one state as the terminal state as well, right? So it has one state and it's terminal. So it has only one step in any episode. So you start with this, let's just, if you, for lack of polite words, dumbest example. And you'd be surprised that this actually works quite interestingly in the real world. This example, and it has a name because it works. It was traditionally the first thing considered. It has a name. Do you know what the name is? So what are you now going to choose from? What are you left with? You have actions and some probability of getting a reward for every action, right? That's all you're left with. So you're in the same state no matter what. So it's like a machine in which you can press one of the buttons or one of the levers, and you get some reward with some probability depending on what you choose. Okay, and so that thing is called it has a name. It has a name which is called multi-armed bandit. Okay, so this exploration versus exploitation business, we will today at least only consider it for multi-armed bandit, and you will see already that the mathematics becomes quite interesting, even in this example. And then probably next time we'll see the more, let's just say, advanced, fancier versions of this. Okay, so that is the plan. So let's me wake this monster up. Okay, and all right. Okay, so Where are they? Oh, why is there nothing here? Okay, there is something here. I just got worried that there is nothing here. All right, so this is what I just told you, and this is the typical picture what one draws about the multi-arm bandit. So it is a good picture. This picture just tells you what's happening, right? So every time you have this one of these things that will give you something back, some reward back, one of the arms. You can choose which arm you want, and then it will give you some reward. Okay, so typically it is modeled that the reward of getting an action comes from a probability distribution RA. So here the capital RA is a probability distribution out of which the reward will be sampled. Okay, so one of them is going to be in the long term the best action, right? The one that will give you the most money. But how do you know? Because it might be that the one that gives you, say, a jackpot gives you only $1 for the first million times and then gives you $1 million. Right? Whereas the other ones are keep giving you maybe $10 all the time, but they will never give you $1 million, no matter what. So it is a little hard to know which arm is the best arm, because there is a probability distribution RA that you don't know what it is. If you knew this probability distribution, there would be nothing to do. You would figure it out and just play according. The thing is, the unknown factor in the real world is you don't know which arm will eventually give you the most money. Okay, so the funny thing is that the traditional literature in this kind of Markov decision-making theory has some very philosophical nomenclature. So let's just get used to the traditional words, and the word is regret. The regret is, in a sense, just the opposite of what we had, the total value. The regret is you don't want to lose too much. So you played this game, you always took hand number 2 and it gives you something, and you had been losing all the while, you don't even realize that. At some point of time you realize it, you will regret it. Right? So that is where the nomenclature comes from. So one thing is that in this case, the action doesn't depend, the Q doesn't depend on an as, because there is only one as, let's just say, this is how this thing really is. So Q depends on an A, and the Q is expected value of the reward given this action. So that is what you want. And of course, one of the actions is the best action, which is, of course, for which the expected value of reward will be the maximum. That will be the best action. So you're at any time, at any moment, your loss. If you take a certain action, your loss at that moment is what you could have gotten with the best action minus what you got with your normal action. That is your loss. This is just a traditional language. So actually, we could have done the same thing with our current language, but it's good to know that this is the traditional language. You'll see this written in many other places too. So it's the same thing, but worded differently. And that way you now have a regret instead of your standard value function. So regret is the best value minus the value you would get by taking a certain action that you chose, time t, right? So then your job is to minimize this regret. Okay. So far, nothing mathematically fanciful, but it will come. It will come. All right. So I actually don't. So it seems. So I mean, I put this slide to demonstrate two facts. Say you can always ignore the first finite attempt. So you took first 20 attempts and you decided that action A is the best action. Then you hit on the greedier algorithm. You always took action A, right? Because that's what your that's what your greedy decision was. But you don't know, right? It could be that the action A was not the most optimal action, right? So there will be a fixed error, a fixed loss in your expected return, so to speak, expected reward every step. So you could accumulate this, and this will be linear, obviously, because every time you're getting the same loss, let's just say over a long time, you have a linear loss in terms of the time steps. In fact, not just the epsilon, if you have a constant, not just the greedy one, but even if you have a constant epsilon, then the epsilon greedy will also be a linear loss. So there is a formula here, I think somewhere between. Is this on this slide? Oh yeah. So I think in this language there is two words. This delta is also your so delta A is the best minus QA. I think it's not, as far as I remember, I have not defined it. So it is, if you take the minimum value of delta A when it is positive, so for the best action it will not be positive, but for the minimum it will be positive, times epsilon would be the linearity factor. Even in the epsilon greedy case, you will have a linearity of epsilon times the minimum delta A not equal to 0. Delta A. So this times the time step number of steps is how your regret will increase as time goes. So even the epsilon greedy, if you fix epsilon constant, will be linear regret. So what should you do to get not sublinear regret? What should you do to get sublinear regret? What would you think? We did something like that already when we did MDP. When we studied our Q learning, did we choose epsilon to be a constant in Q learning? Epsilon was approaching 0. Epsilon was approaching. We chose a glee policy where the epsilons were these factors, and we said that they have to approach 10 to 0, and there is whatever some of the squares have to add up to things like that. So we do want the epsilons to tend to 0 to get less regret. Okay, but in this case, sublinearity is still not guaranteed just by that. Sublinearity is guaranteed. Let's just say when you take the epsilons tending to 0, well, exponentially, essentially. So this is basically the way to get sublinear regret. not a linear but sublinear regression. The idea is very simple. Of course, if you just this minimum of this thing that I just mentioned here, if you can compensate that by choosing epsilon smaller, then at some point of time you will end up actually choosing the correct greedy policy at that time. Right? Once you go below a certain parameter. So I don't want to mathematically explain it because I think it's pretty trivial in some ways, but still maybe it's good to think about it for a second. So your estimate, you actually don't know QA, you just know Q hat of A at some time t, right? And what is it? It is number of the rewards you get, so RT if AT equals A, divided by number of times till this time, how many times you've gotten A, how many times you did the action A, right? So if you did till time t, you have done 100 times the action A. You look at all the rewards when your action was equal to A. Maybe there should be a different parameter here for this sum. So every time t prime is less than t, every time you took an action which was the same as it, count all the reward, divide this average is your Q. This is only an empirical. You don't know what real QA is, but this is just an empirical what you can never get. Okay, so this gets better and better as you go further and further in time. Right? And if you had an epsilon greedy algorithm, which arbitrarily guarantees choosing something, then over large time, you would notice that the guy that has the highest Q will eventually become your best choice. This is. Do you want me to do some simple geometric sum argument? I think you guys are good with that by now. But the idea is pretty much a geometric sum idea that if you want as you go further and further, you will eliminate more and more actions which have. So I have action 1, and its QA1 is its value is less than QA, the best value, by some factor, some alpha. And how long will I keep jumping to it in an epsilon greedy policy? As long as I haven't made the difference, haven't made the fact that this guy has become at least epsilon bigger than this. So you are more or less likely to choose this guy all the time. Right? So this is how the epsilon greedy algorithm works. So this is, if you choose epsilon smaller and smaller, as you said, this is going to converge. So this is not really unexpected. Okay. What is it in this slide or in the next slide? Just 1 second. No, I think I need to go one more slide up. So this has logarithmic regret. I mean, one can do this. It's a straightforward. So maybe I should give this as a homework. Okay, I haven't given any math homework. So if you want to do a math homework, prove that this has logarithmic regret. It is not hard. Okay. But this is a little bit more challenging. So I will try to explain this. So the thing is that you think, okay, we got one algorithm that does a log regret. Can one do any better? Right? Can one do any better? And the answer to that is no. The amount of information you have in general, multi-arm bandit, you cannot do better than a logarithmic record. So that's a non-trivial statement. That's a theorem. We'll come to understanding this theorem by the end of the lecture in some sense. And when we see what the next algorithm we will consider, or next two algorithms, one of which I will explain today and one maybe next time, will show you more or less why this theorem should be true. Okay? But this is good to know, a priori good to know, that you cannot expect to do much better. You cannot expect to do much better, and there is precise formula for this theorem. So there are two factors that contribute in this. So if all the actions were very different, the reward probability of all the actions was very different. What do you mean by being very different? When are two probabilities very different? When their KL divergences are big. So somewhere here, is that written in the slide? I actually don't remember the slides anymore today. I don't know why. Oh yeah. Oh yeah. So maybe there is something that I will explain anyways. So you have action, and there is the action A and B are actions, possible actions. So remember, we are in one step and one state MDP. We don't need any other description. We don't need a state to describe it. We will always be in the same state. After doing either of the action, we are in the same state. So there is one probability of reward that's given by this. Maybe we don't know it in general. This is the reward probability of doing action A. And this is the reward probability of doing action B. How similar are these two actions? What can measure how similar these two actions are? We can measure that by taking the KL divergence of that. Okay? So I want you to, from this lecture, if you are not familiar with KL divergence, this is the one thing I want you to go with confidence out of this lecture, is to remember what KL divergence is. Because this is something, whenever you have, even in supervised learning, if you want to minimize over a density, don't use the least square. Use a thing that measures the distance between densities like KL. So KL is something that's very useful. So if this is small, that basically means that these two probabilities are hard to distinguish. It's hard to say whether this hand is giving you good stuff or that hand is giving you good stuff. Right? If this action is giving you good stuff or that action is giving you good stuff, become hard to distinguish if these two probabilities are close. Okay, so let me just maybe state this. This is not a honest mathematical way of saying this, but hard to distinguish which action is better. And this is the problem. Whenever the actions give you similar results, it becomes hard to distinguish which one is better. So you end up maybe taking the suboptimal action more often than you would like. You will end up taking the suboptimal action more often than you would like, and you will have accumulated more and more regret. Right? So you could be happy with it. Actually, in practice, you can be happy with this situation, right? In practice, you could be, say, if I'm not making 100 million, I'm just making 99 million. In practice, I could be happy with it, right? Because who cares about not making that 1 more million? Okay? Sometimes in practice, you could be happy with the situation where actions have almost the same reward. But still, mathematically, in the very long term, the one that gives you more reward will make if you choose the suboptimal, you will have a regret. Okay. So it's like the time matters, right? So there are people who have, I don't know, have you heard of Warren Buffett? I suppose yes. No. That's right. So why is he famous? Trading stocks. Trading stocks in a very good rate of return, right? But there are lots of people who have traded stocks at much better, almost twice the rate of return as Warren Buffett. But they haven't made so much money. Well, they have made a lot of money compared to us. They've not made so much money as Warren Buffett has. Why? Because he made this money for 50 years. And most people don't manage to keep that pace for 50 years. They do make lot at higher rate for 20 years. Then that's not going to be catching up 50 years of his rate. So two things matter. One is how good your choice of action is, and second is how many steps you do. So whenever we are talking about these kind of things, you should remember that we are always in these kind of calculation considering a lot of steps up to infinity. Right? So you want good actions for longer steps. If the difference is small and you're only taking some steps, it doesn't matter so much. So there is mathematics which I will show you, but there is some practical tactics that one should not forget about this. Okay, so let me show the theorem again. So the theorem says, so if I take one, so if the distance between two actions is not so much, right? The suboptimality is not so much, then 1 over kl is a big number. And that will be having a big impact on the log term here. So if you have almost equally good suboptimal actions, that will actually create some bigger contribution to this log growth of your regret. Okay, so that's something to remember. So we'll not prove this theorem, but by the end of the two algorithms we see today, maybe one of them we'll see next time. By the end of it, we'll realize why such a theorem must be true. So rather than just giving a direct proof, let's go into some algorithms and understand what the thing is. So the main issue today we are discussing is whether one should just stick to a policy or whether one should change, explore more to find more results. So there is a very philosophical phrase used in this context, and I want to just write that phrase first. Forget about the mathematics, just the philosophical worth of that statement is good enough. So both the algorithms that we'll cover in this in this section on exploration versus exploitation kind of thing, or well, maybe we'll call three. Yeah. They all come down to this philosophy. So this is where we explore. Where should we explore? So you have various, well, even in the empty case, you have state action, and that will give you some reward, right? Or in our case, currently there is only one state, so I'm not going to consider a state for the rest of the thing, but you could generalize this thing. So you have an action that gives you reward. I'm very sure about my estimate. So I will have some empirical estimate, say Q hat A. I'm very sure of this, right? So I know very certainly how good QA is. But there is another action A prime, not so sure. Well, this will be the whole point, but let's just say I'm not very sure about this. So even though I'm very sure and it seems to give more reward than that, which one of the two actions should I choose? So it says optimism in face of uncertainty. So if you're not sure of this, you choose this. Even if your current estimate says it's bad, you still choose this. Till your estimate becomes more certain, you choose other actions. Once your estimate is certain enough that it is really bad, that's when you stop exploring. Then that's when you stop choosing it. So the concept here, optimism in face of uncertainty, means as long as you're unsure even of low reward, try to explore it and see if you can get, if your thing was uncertain and you can go higher up. Okay. So now the question is, in this whole thing, what did I assume? What is the interesting thing in when I say I'm very sure of this quantity and not so sure of this quantity? What do I mean? What do I mean and what do I need? What does it mean that you're very sure of something? Any idea? What does it mean to be very sure?
Just try it enough and you know even like the open results each time.
Yeah, you have tried it enough and you have a good idea of what the result is. How do you make it more statistically accurate?
What's the confidence interval?
Yes, exactly. So we have some idea of its confidence measure of how confident we are about it. So this is the next thing that we'll look at for these quantities. But generally, since we are looking only at the example of these bandits, we will be able to compute quite well the sort of upper bound of confidence. We don't need exact, but we need an upper bound on confidence. So the first algorithm that will figure out exactly this thing. So it will be the upper confidence bound algorithm. So what it will do, it will always be able to calculate. It will calculate how sure you are of this. So calculate how sure you are of Q hat. and then apply this kind of strategy. Optimism in the face of uncertainty strategy. Okay, so that is the first algorithm we'll do, and that requires us to calculate the upper confidence bound. So again, it's a question of familiarity. I have included some slides, but it's a question of familiarity of all things. Do you know Markov inequality? Heard of it? Good. Have you heard of Hobbington's inequality? No. Okay. So Hobbington's inequality is what we'll use to get this upper bound in this example, at least. This doesn't work universally, but I think almost everywhere in this kind of situation you will need something similar to Huffington's inequality, and it can be derived from Markov's inequality. So we'll talk about that. Okay, so let's have a look at the slides. So let me also see how we are doing on time. Okay. All right. So firstly, you just sorry. So this slide contains a lot of information, actually. I want to be a little slow with this. Firstly, you want to say, okay, at any time t, for every action A, I want an upper bound on my estimate of how good my empirical QA, so Q hat A is the empirical that we wrote down somewhere, that you can compute by your rewards or how many times you've taken this action, right? That's your Q hat A. How good is it, right? So you try to find an upper bound for that, and consider this Q hat A as some quantity that will compute. Okay. So the point is that you want to say that your upper bound is good, probabilistically good. So you're sure that up to a huge probability, Q hat A plus U hat is actually bigger than what the actual return will be. This is why this is an upper bound. So with a high probability, you want to make an upper estimate on how much you would get by taking a certain action. With a high probability estimate, more than what you would get from a given action. All right. Okay, so and what do? You choose your action. How do you implement this part of the strategy? Choose optimism in the face of uncertainty. How do you implement this part of the strategy? Well, you have an upper estimate. Use this upper estimate to choose your action. Right. So currently, the uncertainty is hidden in the U term. See, either Q is big or U is big. Right? Either Q is big or U is big. So as you choose an action, you choose an action depending on the sum of the value that you think it is giving you and the uncertainty plus the uncertainty that you have for that value. Right. So the more uncertainty, more likely an action will be picked. So this is the part, optimism in the face of uncertainty part. More uncertainty, more likely the action will be picked. Where is it written? Somewhere it is written. Okay. So this is basically the algorithm. Now the question is, how do you compute this estimate of uncertainty. Now, you know there are standard techniques in statistics that tell you how to compute an estimate on uncertainty. One of which is the Huffington's inequality, which will, I suppose, be the next thing. So is there any question on this algorithm? This is basically the algorithm. The only thing remaining is find a function ut using of Huffington's inequality, which we will do in the next couple of slides. Okay. All right. So Huffington's inequality is basically for bounded independent random variable. Although I have included IID in this statement, this is a statement I saw in the literature on the multi-arm bandits. So this is how people in multi-arm bandit usually state Huffington's inequality. But Huffington's inequality does not require your variables to be independent. It only requires your variables to be bounded. And they don't have to be bounded in the same interval. They could be bounded in different intervals. But let's just keep it simple and say they're bounded in the same interval. Okay. Now the thing is that you have a sample mean, which is the first thing you'll compute from something like that, and you have the expectation. And the thing is, how much is the sample mean different from the expectation? Okay, so you say that if I can overestimate the expectation by sample mean plus some constant mu, okay, the probability of that is exponential in how many samples I took and how much the mu is. It's exponentially decreasing by both these factors. Okay. So this is exactly where the n comes in. Like how many samples I have taken is important in saying that my probability is less than exponential in the number of samples I have taken. Okay, this is what you had empirically said, right? You had said that if we do the action many times, we are more confident in understanding. We are more confident in our calculation. So this is actually coded here. But to use it mathematically, you need a formula, and this is the formula. So we'll see some kind of a proof of it. But let's just, I think here is an application. Maybe I should do it on the board, or you prefer it on the slide. I think the slide has this information for you to essentially read it, but. Okay, so what you want is to reduce this probability that that the QA is bigger than your empirical and your bound, which you have to choose. Right, the U is something you will have to choose. And suppose you want this probability that QA is bigger than Q hat A plus U to be P. If you want to bound it by some small number P, this probability, what will this tell you is that you can set P equal to the probability of this being bigger than that. So I think it's written here, right? Is it? Here. I don't have a pointer, I think, but my finger is good enough. P is the probability you want to make this P small. You want to make less of a possibility that this thing becomes bigger. And that should be obviously, this P is obviously less than this number. So I can just take log on both sides and divide by whatever the factor is. And I will end up saying, okay, if I take ut to be this number, I'm good enough. I will be happy. Okay? So if I choose ut to be this number, my probability of having QA bigger than that will be less than P. So that is the simple calculation. This is how you use any such inequality. You want to reduce the probability of something bad happening, you get an estimate for the probability of something bad happening, and try to make this probability less. Okay? So I think the slide, let's just go through this one more step. I think what's wrong? Well, I'll go to this slide first. So just by applying the Huffington's inequality, you get this estimate. Now you want to say that with each step, I want a better and better probability of getting, of not having Q bigger than. So remember, the P is telling you bad is happening. Right? So P is the probability of Q bigger than your estimated Q, and plus U. Right? So as time goes, as you take more and more steps, what do you want this P to be? You want this probability to be smaller and smaller. So you can make this some function which is, I mean, for the log formula we get it's cleverly chosen, conveniently chosen to be t to the power minus 4, but you could choose anything that's becoming smaller polynomially. It will still have the same effect. So you choose P, say polynomially, t to the power minus 4, it will become smaller and smaller in time. And you plug that in your value of P, in the log P, and you get a simple formula for what UTA should be. A very simple formula of what UTA should be. It's only in terms of number of times you have tried the action. Okay? So if you want UTA to be small, what do you need to do in this formula? Log P will grow at a certain way. How will you make UTA small? You'll have to take the action often enough. Okay, so which is obviously not a problem. If you have only finitely many actions, so let's say I take, I have 10 armed bandit. I have 10 actions to choose from. If I have 10 actions to choose from, and I say let's just sequentially take 1 to 10 and then again 1 to 10 and 1 to 10. So at time steps, so my NTA would basically will become T divided by number of actions, right? If I just choose the action in order, just order all your actions and take one at a time, you can choose NTA to be T divided by how many actions you have. Is that good? Making sense? So, and now if I look at log T divided by NTA, that will be log T by T times A. But what happens to log T by T as T goes to infinity? What happens to log T by T as T goes to infinity? This goes to 0. So you can always arrange, there is no issue, at least as long as you have finitely many actions to choose from. And this is anyhow we are working only with not continuous MD bandits, but finitely armed, multiple armed bandits. That you can always be sure that as T goes to infinity, you can make this thing as small as you want, right? For every action. For every action, you can do that. But the algorithm says you take an action depending on certain certain thing to be big enough. So now I have only done is in the last thing I wrote that you choose the argument depending on how big Q is and how big your upper bound is. But now we have calculated the upper bound using the Huffington's inequality. You just substitute that here, and that is your algorithm. That is the basic algorithm for yeah, this is one way of looking at how much you should explore and how much you should not explore. So in this choice of action, there is not just the value of the action that plays a part, its uncertainty also plays a part. So there are two factors to it. Okay. This thing is actually very kind of bleakly described in I think I put a reference book. If you have, I don't know if you guys have seen the book, the Sultan and Robbins book, which I've also given some project sample choices from. The book kind of says, oh, this does not generalize, and so it kind of doesn't care about this algorithm very much. It mentions that this will not be very useful for MDPs. But it turns out that in the years since, people have managed to extend these ideas to various aspects of MDPs, and now actually it's something that more people are excited about understanding this kind of phenomena. So it's worthwhile to revisit this older calculation and understand the basic of how exploitation versus exploration works, because this is currently the unresolved or interesting thing that people are trying to find. So it's not always good to discard old material, because that's where the new ideas come from. New ideas hardly ever come from out of the blue. They always come from some old ideas that people had stopped thinking about. Because at their day, at their stage, it did not make sense to think about it. But when time goes by, you'll be again in a situation where it makes sense to think about the old idea. So this is one of the things. Okay. I have decided to think about it because this by all means is one of the things. So before we go to the next algorithm, let's have a look at Huffington's duality for a minute. So I suppose, as you guys said, you all know what Markov inequality is. And this is a math lecture, so I have to do a little bit of math. So any of you are in math? Or you are in math? Okay. Right? One of you said in math. Three of you are in math. Huh? 75%. Wow, okay. Oh, then if audience has changed to math only, then I'm unnecessarily worried about it. I'm trying to make it so simple. It takes a lot of time. I would not do that for the last two lectures. Oh, sorry. I'm not scaring you. Not scaring you. Okay. I put in a lot of time to think what is scale, how do I explain this, how do I explain that. If I can just state a formula, or you prefer this as well, because all the other math professors are just throwing it at you.
It's not bad if it's slow.
Huh?
It's not bad if it's slow.
Okay, good.
Always good to have some reminder things.
Yeah, because sometimes, one in math lectures, especially if you do this kind of things like the concentration inequalities. I suppose you have had some lectures on all the concentration inequalities. But when you look at all these lectures on concentration inequalities, there is no mention of an algorithm, right? You just do one inequality and it's complicated to derive, and you have to do this and that and jump up and down to get the inequality, and then you forget it. But here, the aim of understanding an inequality is it is directly giving you an algorithm. So So I have written one version of Markov's inequality, which is the version I assume most people in computer science have seen it. So the probability, so x is a non-negative, almost surely. But I don't like to always write almost. Sure. So x is a x takes values in 0, 1, and you want to say what is the probability of x greater than a. Right, so the standardly it's said that it is less than or equal to ex by a. Okay, but there is an obvious version of this. What is the obvious change? What you can do is you can take any function usually called phi. Phi is from 0 infinity to say that for sake of not making any stupid mistake, I'll write 0 infinity on the other side. Is monotone. Is monotone. Okay, and of course measurable. It has to be a good function. So then I could say what is expected. What is the probability of so this probability of x greater than a will then be same as the probability of phi x greater than phi. This will be one and the same thing. There's no difference, right? And if it is one and the same thing, then so again doing this, the things, this will be less than or equal to just by the same old formula. So, so this is what the Markov inequality is. There is a lemma that I will not prove, at least not today. Maybe next time we can prove it. So my goal is not to teach you Hobbiton's inequality or Markov's inequality or any other kind of thing. My goal is to revise them, and my goal is to say this is what goes in constructing algorithms of this kind. That is the goal here at least. But still, let's have a quick look at the math behind this. It's not terribly hard to do it. So I hope I can. All right, so what are we given now? We are given these independent, so there's a IID, and they take value in say AB. Okay? And what I would like to do is so I want to estimate probability of let's just say x minus, where I want it. So expected value, so let's just say x minus expected value of x greater than some t. I think this is how the slide, I only want to be consistent with my slide, but I don't remember what's on the slide. It doesn't matter. You guys can change variable names and all that. So this, by that formula, we know this probability is same as the probability of, so I can choose some number as, any as positive, and so the probability of e to power s x minus expected value of x greater than e to power st. So my original variable was in an interval AB, right? So my new variable, I can still apply Markov's inequality to this, and I know that. So this is less than equal to e to power. So 1 over e to power st I can write as that, right? And the expected value of this thing in between. The expected value of e to power s x minus. Okay, so what Huffington did is he did just this simple transformation and he produced a way to estimate this object, this guy, right? And this estimation is useful. So you can so I'm doing this calculation just to show that often you don't have an exponential in the probability that you are interested in, but you can rewrite it by an exponential. You end up in something like that form. Once you are in that form, then you can use Huffington's calculation, and that is what is called the Huffington's lemma, which is I feel that I might make the screen chalky one day. Is this the right page at least? So what Huffington does is he gives you a way to estimate the exponential probability that are derived you need to know. So if you have this estimation for you, you just plug it in there, do some simple manipulation, and you will get that. Okay. So, well, I did it for one x. You have to do it for all the xi's. Multiply them together, you get the same. It's not terribly hard. So this is the core. And often this is actually the more important thing for deriving your own concentration inequality than the Huffington's inequality. But in this, our example, in the particular approach, a particular algorithm that we had, we got a priori that is good enough. Okay, so this is my background on what Huffington's inequality is and how to use it to produce upper confidence bound. So any questions? All right, so I will now describe actually the how good is the algorithm now, right? So we have now an algorithm. Where is the algorithm? Maybe I should show you the algorithm again. But I don't think I have a slide to tell you how good the algorithm is. Okay, so this is the algorithm which we derived using the Huffington's inequality. And this is again an algorithm with this philosophy where you chose, you have optimism in uncertainty. As long as the uncertainty is big enough that your action is still in demand, you choose it. And when this uncertainty is smaller than QA is, then you stop choosing that action. Right? So this is, and I simply like this phrase, I have to say. I find this very philosophically motivating, optimism in the face of uncertainty. Anyways, it's my personality. Let's just say this is the algorithm, but how good is this algorithm? What do you think? How good should such an algorithm be? Should it be linear? Should it be sublinear? Logarithmic? Of course, the theorem told us that it cannot be. Sorry, it cannot be better than logarithmic. Right? So there is a logarithmic bound to be achieved. And in fact, this algorithm is logarithmic. So in the last bit, I will explain why, just a little bit about why this algorithm is logarithmic, and about how to now modify our situation. So this was the 0th example, by the way, of exploration versus exploitation. This is just building up our mathematical muscles to do the more genuinely interesting part. Okay? It is not the end. It is the beginning of the game. Okay. So by doing all these fun stuff, we have actually achieved a good algorithm, is the statement I want to make here. Unfortunately, I have not, I'm pretty sure I did not put this on a slide. Somewhere I got distracted. And so I have to remember to the best of my abilities as to how big this bound is. So the theorem, if you like, is that your uniform confidence bound algorithm is log asymptotically log t in times about some constant. So this is so it is not the constants are not optimal as far as that theorem is concerned. We'll come to that in the next example, which will actually generalize. At the next iterate of this, so far we have used a very brute force approach, and this brute force approach gives you the idea to the next approach, but it doesn't so generalize. So why should this be log t? Right. So it's basically how your ut is being chosen. So you chose your ut to be square root something. I don't remember exactly. Something like that, right? So this is your ut. Right. And what you know about this is that, so I want to say that in logarithmic time, so as t goes to infinity, arc max a q hat a plus so this is what the quantity is. So this number is going to 0 as we checked while before, right? So and q hat will go to, so we have that qa, the real qa is less than equal to q hat a plus uta, which is we have here. Okay, so this goes to 0 as t goes to infinity. So what does that become? So that converges here, right? As t goes to infinity, if your action is so I'm writing this very crudely right now. Very, very crudely. So this converges to here. So as t goes to infinity, what you see in this argument that this actually will converge to the actual. So this will converge to arg max or a of actual qa. This will converge to V star. So your choice at infinity is the best choice. Okay. Now the question is, are we improving this during the process? Are we improving? How much regret are we adding up? How good are we jumping? So the thing is, so now I want to estimate, or do I want to do the whole calculation? Let's see. Okay, that's good. Because actually I'm wondering if it is actually teaching us anything. It is not going to teach us anything except for the fact that we can manipulate logs. But what it has to teach us is something else. So what we want to learn from this, okay, you could add up this thing cleverly, which I will probably not do. So you have this estimated QA. So your estimated QA at any time will be Q. So your QA star minus Q at AT, given that AT was chosen like that, is less than equal to Q hat A star plus square root. Because you remember what Q hat A star has to be less than, with a high enough probability, has to be less than, I want to. Okay, so with a high enough probability, Q A star is less than that, and I will put the probability factor here in a second. But let's just write one thing, minus QA, minus QA. But QA is also in some ways about. So this, when I look at argmax of this is AT. If this is great, then this should be greater than now I'm confused. I don't read what I write. And you read what I write? Or do I do this again? Anyways, forget about the manipulation. What you end up doing is you're ending up summing up square root log t over nt. And this sum, because it's a square root over 1 over t times log t of sum, it will be a log term. Okay, so I can do this calculation for a little bit and explain you this, but or maybe I'll just add a slide. It's much better. But this is not surprising after you replace this calculation, which is what you want to do, that this minus this should be this times this. Add up all of these terms when you have log and NTA, you'll get log t term. So I'm getting a little confused at this moment, but I will add up a slide with it. So that will be how you get that this is a sublog estimate. So what did I want to say? I'm going to skip this, add a slide for it, but what I want to say is it is teaching you something very valuable. It is teaching you to treat this difference between QA in Q star A. So it's teaching you to treat this as a probability. So it teaches you to treat. So you're choosing. So now you want to say what is the probability of choosing the action A given all the data. So this is the history at time t. Always H will always be history. What is the probability of choosing an action AT at time t? It is given basically by your estimated the probability of the Q hat A being bigger than Q hat A hat for all A given the history. So this calculation is saying that Q hat A was bigger than everybody, including Q hat A star, and it was bigger, and that's why we chose this action A. And we chose this action, the probability of choosing any action at any historical point is basically turns out to be something of this sort. So this is what the proof actually teaches us, but I kind of miscalculated something, or in my head I'm miscalculating something. So this is what you should be learning from this proof. So if you learn something like that from a proof, what should you say about that? Let's call this our new algorithm. So rather than having to compute the confidence bounds to get this precise formula, we have this empirical object QA and Q hat A, and let's compute empirically, at least, or by other means, what this probability is. Okay? And that should be a new algorithm. So this is sometimes called, there is a name for this, and this is often used in machine learning. And I think there is a whole family of such algorithms called the probability matching algorithms. I'm not an expert on this. Absolutely, but I can look at some stuff up before next lecture. So this is what this thing is doing. It is matching the probability of making one value estimate bigger than the other value estimate given the history as the probability of taking an action. Okay, and so this gives you essentially a new algorithm, which is the probability matching algorithm. Okay. So more or less, if you do this with a clever probability matching algorithm, if you have a clever way of sampling to compute this pi of choosing an action. So if there is a clever way of sampling, to get good estimates. Then that will be the algorithm. And that is an algorithm to actually substitute how to choose your action, right? Choosing an action is the balance between exploiting and exploring. And what you will choose is you'll choose an algorithm for which the probability, you choose an action depending on how probable it is to get QA to be bigger than QA. So could be that your action has a higher rating here only because we are uncertain in its estimation. right? The probability of choosing an action here, it probably is a suboptimal action, but he chose it. Why? Because current history says it might be a better object than anything else. That is what the current history tells us, right? So in some ways, you choose an action, then you have a better estimate of its value. And once you have a better estimate of your value, you basically know if it is in fact a better action or it is suboptimal, and you discard it eventually. So as long as you are less certain, your action will be picked by such a probabilistic approach. Okay, so this is again the same phenomena. It is the phenomena of optimism in the face of uncertainty. Okay, so maybe I will do a lot of Bayesian. I didn't want to start this right now, but don't we even have enough time for it? I suppose. Okay, 1 minute is certainly not. But this requires a good interpretation of this requires some background in Bayesian inferencing. So next lecture will be a lot more math, and it will be online. Okay, I'm not physically here in Vienna next Friday, but this is the mathematics I actually wanted to cover for this course. So I would be very happy if any one of you are interested. And the week after, we will be here for the last lecture. And we'll probably do a whole bunch of summary things. All that is left, sort of outlook summary lecture at the end. Okay. But next week will be a further elaboration of this using Bayesian invariance, and it is online. Okay. So well, that's for today. I'll add a slide here. What is this? It did.